I've already heard this is National Chemistry Week. This is the Delta College Chemistry Department. Well, most of us. Where's Barbara? Barbara's over there somewhere? Oh, there she is. All right, so this is Delta College Chemistry Department, plus our own San Joaquin Delta College American Chemical Society Student Club. Beth, please give them, this is in conjunction with them, this is all what we're trying to bring to you, the excitement of chemistry, the magic of chemistry. So this is part of what we do. Our first demonstration, we're gonna do a little magic since we're talking about the magic of chemistry. And we have Kiara, Felix, and Jen. And as we can see here, it is completely blank. And I want some oohs and ahs. I better hear a lot of oohs and ahs here, because this took me, well, I didn't do it. You guys did, right? It took like, what, 10 hours to do or something to get this all. You had to make everything. So even the paper, they made the paper. Can you believe it? So we're going to see some magic occur here. Wow, look at, no, I mean, seriously. There we go, that's what I want to hear. So how do we do that? So who is taking chemistry in the audience? Who's taken at least introduction to chemistry? I like that response. What was one of the compounds that turned pink that you guys used at some point in time? Permanganate, but it turned pink during one of your favorite things that you possibly did maybe over and over, and then it turned pink too soon and you had to do it again. During titrations. Oh, you guys are, come on. Phenolphthalein, so this is a phenolphthalein indicator, and we sprayed sodium hydroxide, which turns pink when we do it. Magic cups, are we up? So, we have a magician here. We have the magician. Are you ready to demonstrate this? All right, I'm going to hold the mic. All right.
So, I have a graduated cylinder right here, the big one. I will be filling it up to 100 milliliters of water with deionized water.
I'll hold on. That's a lot of water.
After I filled up the graduated cylinder, I'll add 15 drops of phenolphthalein.
There's a pH in there somewhere.
All right.
Well, that didn't change any color. It doesn't look like you're doing anything to it. I thought this was magic. Oh, sorry, it's coming.
All right, so after I do that, I will be adding sodium hydroxide in this mini graduated cylinder, 0.1 meter? Molar.
That's a lot.
And then in the second mini graduated cylinder, I'll be adding hydrochloric acid, 1 molar. And if you guys can't see in the back, I have 3 blue cups.
Magic cups.
Magic cups. And in each one, the first one I'll add sodium hydroxide. The second cup will contain hydrochloric acid. And in here I have 2 grams of sodium polyacrylate, and that will be added in the third cup. Okay, so you guys see that I'm holding this graduated cylinder full of water and phenolphthalein.
Phenolphthalein.
Phenolphthalein. And in this first cup of sodium hydroxide, I'll be dumping the water in it, and there will be a reaction in it to where it will change a certain color. What color do you guys think it's changed into?
Yellow.
Right.
Well, let's find out.
All right, I'll show you guys. It turned pink. Girl. And in the second cup of hydrochloric acid, what do you guys think would happen?
Turn blue? Who thinks we're blue? Purple? Rainbow color? Okay. Let's find out.
Right. You guys ready to see? All right. It neutralizes into salt water.
I'm looking at you 1B students and organic students, and I'm just sitting there shaking my head, just moving my head back.
Okay, so in this last cup, what do you guys think would happen?
It's gonna blow up.
That's a good guess. I like that. We're having an explosion. How about that?
All right, so I'm going to add it in here. So do you guys think it changed the color? Yeah? All right. Ready?
Wow. How did you do that?
It's called magic. And basically what this is it is sodium polyacrylate, which is used in babies' diapers that absorbs all the water in their teeth and everything like that. So yeah, that's what it is. Thank you.
Thank you. Next up, we have our own very Dr. Demarnik and Nia. They're going to be looking at what dry ice does. So we might even find out what dry ice is. I was always wondering, how can you have dry ice?
We were wondering about that too. I'm Dr. Demarnik,
I'm Duncan.
and we are going to tell you today about universal indicators and show you how they work. An indicator is a compound that changes color depending on whether it's in an acidic or a basic medium. Do you guys know what an acid is?
What's an acid? Somebody said it back there. I want to hear it. Any definition, anybody. Shout it out.
Donate hydrogen.
Donate hydrogen.
Where does donate hydrogen? Who says donate hydrogen?
All right, so acids donate hydrogen, and what about bases? Come on, I see you guys in SI. Let's go.
I mean, if they're an SI, I hope they're doing a Lewis acid base. Well, maybe not.
So yes, bases, they are able to accept protons.
What's the difference between a proton and hydrogen? A proton is, first of all, is an elementary particle that's found in nuclei of all atoms. But also, for the simplest atom, hydrogen, 99.98% of hydrogen atoms have just one proton in their nucleus and nothing else. There are also some isotopes of hydrogen that can have a neutron or two neutrons, but most hydrogen, only one particle in the nucleus, and that's the proton. So the proton is also an ion that is formed when a hydrogen atom loses an electron. A hydrogen atom without an electron is a proton. So depending on the concentration of protons, acid-base indicators will display different colors. And we are going to use a solution of a universal indicator. That's a mixture of several indicators, and we expect it to go through a change of colors. And let's come back to Dr. Kim's question. What is dry ice? So right now, Nia is mixing the solution. This green beaker will contain the universal indicator.
It's safe, guys. Don't worry. It's safe.
Good catch. So as we all see, the very first thing is safety, which we should all have our goggles and gloves on. I forgot my gloves.
Always goggle.
Always goggles. The other thing, the universal symbol for distress is your goggles on your forehead. There we go.
Neck protector.
So as Nia is mixing the solution, I'm going to be looking at this dry ice. As you can see, I'm using a hammer. I have a chunk of dry ice in here, but I need little pieces, so I'm going to put it on the floor and break it down. Dr. Kim comes here.
Very rarely.
Okay, we'll keep it in mind.
All right, so this is a solution of NaOH. If I pour this universal indicator, what color do you guys think it's going to be? Purple. All right, let's see. It might be orange. I don't know. Let's see. Ooh. Stir it up a little bit.
Great lesson in the mean free time.
We love color purple.
I tried to explain to them that, like, even in rivers, there's concentration gradients. They can never understand. It doesn't make sense.
Okay, so we're going to start adding little pieces of dry ice. Would you like to do it? Let's see what happens. Little chunk, big chunk can do too much.
So I like to call this TV chemistry. You'll see why. See the bubbles? Look at the bubbles, look at the bubbles. Every TV set, they always have this bubbling something, cauldron. And every time I look at it, I just think, I can be a TV chemist too. All I need is just some dry ice, some base, and some universal indicator. So, we see what's happening, we see the bubbling. If you guys didn't already know, dry ice is basically solid CO2. And what happens is, because it's left out in the temperature that it is now and the atmospheric pressure, it's able to sublime. Now, you guys see the change? See what's going on is that it's still subliming. The CO2 is turning into actual carbon dioxide gas. And as it's doing this, as you guys can see, it's able to dissolve into the solution. Now, if it's dissolving into the solution, why do you think that is? Why do you think the color's changing? Anybody? pH? Did somebody say pH? Yeah, somebody said pH. I heard it. Yeah, somebody said it. And basically, yes, the pH is changing. It's suddenly increasing. So then, because of that, what can we say about dry ice then? It's acidic. Yes, it's acidic. It's a weak acid that's going on. And basically, this is an acid-base reaction. And you can see it as the colors change because of the universal indicator.
Yoo-hoo!
He just experienced a lot when we experienced when we asked questions. It's like, so what was it again? I don't know. So, great job. We have up next Dr. Reedy with his amazing Pringles cans. We have two assistants, Carlo and Clarissa. They are going to be doing this very famous demo of his. This will have a slight noise. So, if you want to apply those earplugs at this time, that would be a great thing to do. If you don't mind, not that they have their own protection or anything, just to kind of point that out, but take it away.
All right. Before we start, does anyone here remember the Hindenburg, 1937? Yes? What happened?
I do.
The first in the flames.
Ouch.
The first in the flames.
You were.
All right. What was the Hindenburg?
It was a Zeppelin.
It was a Zeppelin.
Blimp, basically.
Yes, it was a flying airship. What was it filled with?
Helium.
Helium? Was it filled with helium?
No.
No? Does anybody know? Oh, did I hear it? Hydrogen. The Hindenburg was filled with hydrogen. So, while I was giving you a history refresher, Clarissa is filling our cans with hydrogen gas. And what are they going to do, Clarissa?
Okay, so we've now filled up our cans with hydrogen. We have a hole at the top of each can, and as soon as we take off the tape, we're going to light it on fire, and we're going to see what happens. Are you guys ready? All right, we're going to put our hearing protection on, and we're going to get ready for this explosion.
Yeah, so remember, we just mentioned the Hindenburg, and they're going to light that on fire. So, Dr. Eady, why didn't they explode?
That is an excellent question. Who can tell me why a can filled with pure hydrogen didn't go blow up the second they lit it? What's missing? There's no oxygen in there. Now, at the bottom of the can, there is a hole that lets air come into the can. And the top hole lets the hydrogen come out of the can. Although you can't see it, I can feel that burning flame on the top. Slowly, the air and the hydrogen is going to mix together. When it reaches just the perfect mix, and it reaches that flame, the can's going to start whining to let us know it's ready to go. 15 seconds after that happens, plug your ears. Let's listen up, guys. Anybody see it? I don't hear any whining yet. Oh.
There you go.
The longest 15 seconds of your lives. All right, up next, one of my favorite demonstrations. I'm doing it. I'm doing it. You doing the talking? You're doing the talking? All right. We have, well, Antoinette's going to do the talking. You can introduce because I lost my page. Go for it.
Hi everyone, good morning. So my name is Antoinette. We have Gerald and Ivana. Who here this morning has brushed their teeth? Everybody's hands better be up. All right, so as you guys figured, elephants also have toothpaste, and obviously they must brush their teeth. So today we are going to be making some elephant toothpaste. You guys are probably like, what is that? You guys are gonna find out. So here we have a solution, and we mixed it with soap. This is our little concoction. And we have another solution, which is potassium iodide. Does anybody know what potassium iodide is? Potassium iodide is a catalyst. Does anyone know what a catalyst does?
Speeds up a reaction.
Exactly, it speeds up the reaction. So normally this reaction is pretty slow, so we're gonna have a bunch of iodine to speed this up because we don't want to be here all day. So we're gonna add our food coloring. All right, now that we have our little concoction ready, we are going to add our catalyst, and you will see the toothpaste form before your eyes. 1, 2, 3.
as you guys may have seen, you can see right now there's some heat that's coming off. Does anybody know why there's heat coming out of it? What kind of reaction? It's an exothermic reaction, which means the heat is being produced off. So this reaction is actually very hot. So yeah, elephant toothpaste.
So we have the duo here. We have Brenna, who's going to tell us a little story, and we have Dr. Mary Ellison, who's going to be the assistant this time, I guess? Or are you the, okay. So, take it away.
Hi, my name is Brenna. This is Dr. Ellison, and as you can see, she's holding a kind of strangely shaped bottle. So there's a little backstory behind the bottle. So last summer, I went to Asia, and I was taking a cab back to the airport. The cab driver gave me this bottle, and he said that it was just a parting gift, and that I should be very careful not to rub it because something very, very bad could happen. So of course I didn't really listen to him. So I brought it here today so that we could see what kind of bad thing can happen. So, Dr. Ellison, would you mind doing me the honor of rubbing the bottle? So as you can see, it's smoking right now. And if you remember the same principle that they used in the elephant toothpaste, where the manganese chloride dioxide or magnesium chloride oxide is a catalyst for the hydrogen peroxide that's sitting at the bottom of the bottle. So does anybody know why she's holding a glove right now while holding the bottle? Exactly, it was an exothermic reaction. All right, thank you.
Next up, we have a demonstration that we do not do at home, so do not replicate this at home. We have proper safety precautions here, at least we try, so that's why we're doing this in a certain way. What we're going to create here, I hope, is we're going to create some bubbles. And these bubbles are going to have a little bit of a different composition than you're normally used to. So in the bubble bath, you know, you take a bubble bath, relax tonight, sit back. The bubbles typically have just regular air in it, so that's just created from the air that's in the atmosphere. We actually filled this ball here, don't pull too much, with natural gas, actually the gas that we use in the Bunsen burners, so on and so forth. And what we're doing is we're trapping that gas in these bubbles. Now, if we're careful enough, and we take proper safety precaution, we use enough protectant film, kind of like that you see a lot of times people get slathered down when they have a lot of heat. You can see our hopefully flame-resistant students over here, we'll find out in a little bit, are protecting themselves with this special sort of solution of soap. Okay, well, let's see if it works. I hope they don't light on fire. We'll find out here. So, let's see these brave volunteers pick up these bubbles of a flammable gas. And who's lighting? Am I lighting? Or is she lighting? All right. Did it burn? So get more, we want higher flames, so we get a lot of bubbles. We can see this thing burst into flames. Now, we're using proper protection here because the soap is going to act as a barrier that's non-flammable and has that nice little coating ability so that it won't actually burn through their hands or actually cause any damage. So, but don't just try this at home, think, I know what I'm doing, I saw this demo at San Joaquin Delta. We practice this. All right, there we go. We need a lot more bubbles. Usually a lot more. That's all right. All right. One more, are we good? All right. We're good? All right. Thank you very much. Notice safety first. Dr. Cardez. Yeah. Are we ready? Are you, where's the extra mic? Where'd it go? Here's John's. Oh, here you go. Anyone else talking?
I turned it on first.
No.
Well, good morning. My group is going to show you several demonstrations that involve liquid nitrogen. So liquid nitrogen is a gas room temperature, and 25 degrees Celsius in 1 atmosphere is a gas. But we have liquid nitrogen, so it's a very, very low temperature. So we have Maria, Brandon, and Amadari that is going to tell us about liquid nitrogen.
So one of the most interesting about water is that when it's frozen, it actually expands. And when cells are mostly made of water, it'll actually expand and freeze over. And what do you think is going to happen when your cells actually get frozen? You got a second one. All right. Sorry about that. I guess it got sun stuck.
So Maria, what can you tell us about nitrogen?
So liquid nitrogen is, it's cold. It's really, really cold. It has a boiling point of negative 312 degrees Fahrenheit or negative 196 degrees Celsius.
So you can see that the rose was at such low temperature that it became brittle. So that's what happens when we put any tissue in liquid nitrogen. The temperature gets so low that it's going to freeze. So it gets solidified. So it's going to become really, really hard. So we are going to show you something that you have never seen, and that is a banana hammer.
This was just a regular old banana, soft and squishy, but if you, can you put the mic? Cold it is.
Didn't know your own strength, did you?
Hey guys, my name is Amarani. So I'm going to be showing you guys a demo with this balloon. So I have a quick question for you guys. What is the most common gas in air? Okay, alright. So liquid nitrogen is made by taking nitrogen and putting it under pressure until the gas becomes a liquid. So what we're gonna do is we're gonna submerge this balloon in liquid nitrogen. As you guys can see, it's pink, right? Do you guys think it's gonna change any color? What's gonna happen to it? White? Okay. So when we put the balloon in liquid nitrogen, the air molecules inside slow down because of the temperature is so low. So with less molecules going together, the pressure also decreases. With less pressure, the air surrounding the balloon makes the balloon shrink. So I'm gonna go ahead and take it out. What color do you guys think it's gonna be? So liquid nitrogen The nitrogen in the liquid makes the balloon have icy crystals on it. When we take it out, the balloon goes back to its original shape because the air surrounding it warms it up. So as you can see, it's going back to its original shape.
Okay, so the last demonstration, we are going to have Antoinette. Where is she? Okay, so we are going to show you what happens when liquid nitrogen expands.
Do you ever have a juice box? Like a Capri Sun blow on you, you blow the bubbles in, what happens? What happens when you blow bubbles into the Capri Sun? It squirts out. Why does it squirt out? What did you increase in there? The pressure. Guess what happened to all of that liquid nitrogen? Well, Dr. Carr has talked about the fact that it doesn't want to stay a liquid, it wants to be a... And so what happens, I'm going to scoot around here, is we're going to use that same concept, except we're going to do it really fast. We're not going to wait any time like that one. We're going to do this really fast. Now, if you're in the front row, you may get a little wet. If you've seen Gallagher, I'm sure none of you know who that is, so I don't even know why I mentioned that. But anyway, you know you want to have like drapes on you and things like that. You might get a little damp, we'll find out. So instead of taking a very short period of time, we decided to do it extremely quickly. So what you can see there is the pressure builds up again, and we have that. Anyone get wet? Yeah, I did too. I thought I was far away from there. And so what you can see is just the leftover liquid nitrogen, again, just going from that liquid state to that vapor phase, almost directly through our little experiment. Any guesses on what this white stuff is? Smoke. What kind of smoke? Where do you think you see those? Do you think this is dangerous? Where do you think it is? It's water vapor. It's cloud. All we're doing is it's so cold that it's taking some of the water in the air and actually just creating a small little cloud out of it. Up next, we have, where did we go? Where am I? Chemical flares. Dr. Little. Yes, he's done this for many, many years. He's actually one of the experts we have on these chemical demonstrations. If I have questions, I always come to him. So he's going to take it away.
Okay, we have
John. Edward.
Anne.
Heinze.
And what they've done is mix some sugar with some potassium chlorate. Potassium chlorate's an oxidizer. And in each of their 3 separate containers, they also have a particular metal. When they put sulfuric acid, this is the dangerous one, when they put the sulfuric acid that they're holding now on that mixture in the pan, the sugar will cause the potassium chlorate to get hot. Potassium chlorate will catch on fire, and the metal will get excited. You're going to see the result of each different metal responding differently, but think about it. If somebody mixed you with sugar and then set fire to you after they poured acid on you, wouldn't your electrons jump around? Yeah. These are chemical flares. This is how fireworks work. Notice they are extremely careful. And we see you have 3. Okay.
Those look like purple to me.
Strontium and John, you had
It was strontium, potassium, and
potassium. Okay. Yeah. Okay, there you have it. Chemical flares.
I have 2 contestants. Can't take them from the audience, but we have 2 contestants that volunteered this morning. Are they in the are my 2 ACS volunteers here? Where are we? Where are we? Where are we not here? All right. So we're going to do a little bit of a race. Now, you can't run because we just destroyed this hole down here. But what we're going to do is we're going to have a race. And your jobs are going to be to fill up a container. And the container is going to be filled with styrofoam peanuts. That's pretty easy to do. I mean, that's not hard at all, right? So we have our styrofoam peanuts right here. So what we're going to have is we're going to place this directly in the middle. And your job is you're going to run back and forth. Well, okay, we'll say walk. Let's not run because we don't want anybody wiping out here. And what we're going to have is we're going to have 2 containers. And your job is going to be to fill them up. As I trip on that. Where are my 2 containers? You don't have your 2 containers. Did you find Ginza? All right, there we go. We're going to have 1 over here. What happened to my water? Where'd that water go? Oh. About how much, Ginza? Halfway? And we're going to even give you guys a little bit of an advantage so it doesn't take as long. Your job, as quickly as you can, is place these styrofoam peanuts and fill up that container. Whoever fills it first, what chemistry are you guys taking? 1A, who are you taking with? Dr. Day, where is she? We'll tell her you get the A, how's that? We'll convince her you guys get the A. You ready? You're going to take those peanuts, you're going to go to that one, you're going to try to fill as many peanuts you can on that one. You're going to take the peanuts at the same time, not running, and fill up your container. Are you ready? I mean, this is for an A. You guys are not very excited for an A. I mean, seriously, an A in chemistry. Who would want? I would want an A in chemistry. I mean, I may have to convince Dr. Day of it, but that'll be easy. On your mark. Get set. You guys are seriously, come on. I mean, this is an A. Go. Oh, she So I always forget about that part to mention. You can't pick up the kid. Oh, we're gonna try to do that. It's just not working over there. Uh-oh. What? Hers is not working very well, is it?
Looks full to me.
You're still not filled up. It keeps on going lower and lower and lower and lower. So, you didn't even make it worse. You stacked it even pushed it further. So, I don't think that is going to happen now. So, fairly filled up. It filled up fairly well. Except it keeps on having popping up. But what's happening over here? I mean, we kind of gave you the bum one here. What's exactly happening? Well, styrofoam is what we call a polymer. And what we have in there is we kind of, by accident, we poured acetone in there instead of water. I mean, the gels were supposed to be labeled, but I guess they weren't. And so acetone Actually, some of you might know, this is typically used as a fingernail polish remover. Well, it does almost a very similar thing with styrofoam. It causes it to dissolve. And so thank you very much. I'll try to convince her 2 ways how that goes. We'll see if that goes okay. Next up, we have Professor Devins, who is going to actually pull a polymer. She's going to actually create something similar to this styrofoam, just a little bit different, but she's going to actually create a strand of this polymer from 2 liquids. And am I holding and you're just going to talk? All right, so we'll do it again.
Actually, what I'm going to do is pull nylon out of a beaker, just like the magician pulls a rabbit out of his hat. Now, most of us have no idea of what nylon is because you're not of my generation, or you don't know Joe Namath. As far as looking at those who know Joe Namath right there, famous sort of quarterback, who did a pantyhose commercial with nylons after he quit being a famous quarterback. And so, but nylon is a polymer. And it is actually a very important polymer. It's a polymer who made one family extremely rich, the DuPonts. Because they developed it after, in fact, for World War II for 2 reasons. One, because of the fact that we were no longer getting silk from Japan during the war, and that we had to have parachutes, but we also had to have something to replace silk stockings. Another thing, which if you're not part of my generation, you have no idea what those are either, to take a look at. But I'm going to pull this nylon out of the beaker. We add our different chemicals, not really measuring things out. But as I add my first chemical, the first monomeric unit, polymers are long repeating units of compounds, some good, as we know now, some bad. They're polluting our environment to no end. All of those plastics out there. Besides the chemists, we are a member of the Sierra Club. And we pour in our second monomeric unit. And one notices at these that they are just like with those of us in my class, the 2 compounds that are not miscible, that we have here a reaction occurring at that interface. In which we can pull that material, can hook that up, and I start to pull my long nylon rope out of that huge mixture, a long, continuous molecule, which then can be refined into those famous Joe Namath nylon stockings. And we can continue and continue and continue for a long time until we run out of one of those monomeric units. So I keep pulling that long, continuous polymer that we have everywhere, forever and ever and ever.
Thank you. Check 1 2. That pretty much brings us to the finale here. So, where is Kendra? Jacob. You guys, where are you two? So, you may have seen this demonstration done before. This is the second to last. This is one of our big finale demonstrations. We would request help picking up. So you should automatically be like, I wonder why he's saying I'm picking something up. So we would request if anything goes flying in your direction, hopefully it won't, that we can get the assistance of picking any of these things up. I don't know where pins are. Okay, so we're on pause moment at this point.
Tell some jokes.
Tell some jokes. I don't want to chemistry jokes. Yes, sir. Dr. Reedy has one for us.
Neutron walks into a bar and asks the bartender, how much for a drink? Bartender says, for you, no charge.
You guys get it? I don't get it. Mushroom walks into a bar. Mushroom walks in the bar. Goes up to the bartender, orders a drink. Bartender says, we don't serve your kind here. Mushroom says, why? I'm a fun guy. That's all I got. I don't know. I'm not. Ken's waiting. Oh, there she is. So, you may want to cover your ears. This will have a little bit of a shock value to it also. So just be forewarned. Again, we are doing proper safety. This will be a little bit loud, so you may want to cover your ears and so on and so forth. If you can't tell, we like playing with liquid nitrogen. And fire. I do. How much did you put in there? Do not do this at home, obviously. Last but not least, because I can't catch anything, I shouldn't have said anything. Last but not least, where is Dr. Julius Hastings? Are you up there? Are you going to stay up there? You're staying up there. Okay, so last but not least, as we said, we like playing with liquid nitrogen. You saw that. We also like playing with fire. And yes, we do like playing with fire a lot. So we're going to do some last demonstrations that require a little bit of fire here. It's not the police, hopefully. They're already here. Oh, that's right. I notified them this time. Last time we didn't notify them and it was not a good idea. We lost our candle. Has anyone made it in yet? I keep on seeing all these balls flying, but I don't think anyone's made it.
I almost had it.
You almost have it? Yeah. That's like the biggest applause we had all day. I mean, that's kind of sad. I mean, I thought that last one was pretty good, but I guess... No, never mind. I played hockey, I didn't play basketball. So. All right. So what we're going to do is we've filled these balloons with nice, flammable material, which we always enjoy to do. And so what we're going to do is we're going to, or I guess I'm going to, Should be a joke right now. How many chemists does it take to undo balloons?
I mean, my legs are like down here.
I know it's here somewhere.
There.
All right. So what we have is this nice little flammable balloon here, and I guess I'll kind of solo this for a little bit, see if I can do it. And we're going to light it on fire. As people are throwing things at me, if you're in my class, 0, because you missed. That's right. So you guys didn't know I was a comedian too. Julius, I need your help here. All right. See, no, almost. See if I can do this solo here. Nope. Ready?
That's awesome.
Maybe I can't do it solo. You want to hold my? I got it now. Or you want to take over? All right. Should we have? See, this is yeah, it's off. So we're gonna try some more. We'll see what happens. We'll try to go from, because that was pretty big. We'll try to go bigger and bigger and bigger and see what actually happens. We could actually be a little more dangerous and actually directly do it, but let's not do that. Do the orange one back away. So, all right, let's see if we can do this again. You want to do it? All right. It's not on there very well, so don't sneeze, don't move. Go for it. The suspense. I think, oh, no, still have. I don't think you have a flame. Get a little gun shy on us here. All right, well, hold on. Let me get out of the way here first. I mean, this one's a little bit bigger. So, do we want someone, let's see, should we have Trini do it? No? Why not Trini? How about one of the police officers? They're used to these big bangs. I mean, they go to target shooting, everything else. Maybe they'll be a little less gun shy because we had a little bit of shaking there when it comes to this. So we'll see. So we need protective goggles. So let's get her a pair of goggles. Oh, here's the goggles right here. I know we'll just hopefully get no hairspray, right? No hair product at all. Well, yeah, we'll see what happens then. I'm just going to back away and hope for the best. So what you want to do, this is right where that string is, hold it up to that. I know, it's going to be difficult. We have faith in you. So close. Oh, the suspense for... Sorry, great, thank you, Joe. That was helium. So the other two were actually hydrogen, and so when that actually reacts with the oxygen in the air, that actually creates... What's hydrogen and oxygen make together? All that bang was from water. All it did was make water. That's it. So, again, we thank you for coming. We hope you enjoyed yourselves. We'd like to thank Trinidad, who is our stock administrator. Without this would not be possible at all. Without her help, her guidance, this would be nothing. This is all because of her, so she deserves the big round of applause. The students, thank you for volunteering and for practicing. You did an excellent job. The professors, yeah, you guys, I got you. Have a good day. Thank you very much, and we'll see you next year, hopefully.